Okay, we're looking at what's called a system of linear equations. And the way I explain this is that a system of linear equations is like a Marvel movie. It means that more than one line is existing in the same universe, or in this case, it's on the very same graph. So let's take a look and I'll show you what I mean. So what we're trying to do here is at first to see that if two lines hit each other, if they intersect, the point at which they intersect is called their solution, the solution to that system. Now some lines don't intersect at all, which we'll talk about later, but if they hit, that point is called the solution. So the first thing we need to do here is if they're going to ask us, hey, does this point, is this a solution to the equation? And what you do is you put it on both lines. You put that x and y coordinate into both lines, and if it's true, then this is true for the entire system. It means it must be the point where they hit. Okay, so let's try one. So we're putting in the point -2, -1 into both equations. So we're going to put this in. We're subbing in -2 for x and -1 for y, and we're crunching it down, and we found that what we have is telling the truth. -1 does equal -1. Okay, so far so good. This is true. Now that means it's on one line, but it doesn't mean it's on both. Let's try again. Let's put those points into this second equation. And when we crunch it down, notice the order of operations here. I'm subbing in, so I'm putting in parentheses. I got double negatives. I get 5 equal to -5. That's not true. So this point is not on both lines. It is not an intersection point. It's not a solution to the system. Okay, now let's try this one into those two lines. So I'm dropping -4 in for x, -3 in for y. I'm crunching that down. I get -1 equals -1. Well, that's true. Okay, so far so good. Now we put it into the second point. We crunch down our math, and we get -5 equals -5. That is true. So we have it true in both. It's on both lines. It must be a point where they intersect. Okay, you can always try this on your own. Let's take a look here. I'm putting in 1 for x, -3 for y. We're doing this A one here. That's supposed to equal 0. Well, let's see if it does. It does. So far so good. Now, if it hadn't, we could have just stopped right away. We would know this isn't going to be a solution. Let's put it in the second one. All right, I get 1 minus 6 equals -5. This is going to be a true as well. So it's true there. It's true there. This is a solution to the system of equations. Now let's try the second point. I'm putting in 0, 0. That's going to be true, right? Now let's try it in the other one. Okay, that is not true. So this second point is not a solution. They don't intersect here. Now here are the possibilities. You could find that they intersect. You've got that solution there. Or can you see that parallel lines are never going to intersect? And then lastly, you may find out you have the very same line, and so they're touching everywhere. It's literally on top of each other, and so there's an infinite number of solutions. So this one, parallel lines have no solution. This has infinite many solutions. Okay, so let's just, not everything is on this problem, but if we graph two lines and we look where they intersect, the point 4, -1 is the solution to the system. That's where they hit. Now, we're going to learn 3 approaches to do this, but the first one we're going to take a look is we're going to do this by graphing. Now, you can graph this multiple ways. These are in standard form, so doing the x and y intercepts would be an easy way to go, but I'm going to rearrange both of these equations so that they're in slope-intercept. Now, I'm dividing both sides by -3, so do you remember that's going to make... So I divided this entire right side by -3. It's got to go into both of these. Okay, now let's graph this. I intersect at 1. My slope is up 1 over 3. Up 1 over 3. Up 1 over 3. Okay. Now the reason this is a difficult approach is because making those lines look nice and perfect so you can actually intersect on the grid can be rather challenging. Now I'm taking that second equation, I'm putting it in slope-intercept form. Now the y-intercept is b. Do you remember this has a slope of negative 1 over 1, so down 1 over 1, down 1 over 1. Okay, so I got this right here where you can see. So the problem is it's hard to get at an intersect point because you're not a ruler or a computer. But so here we go, and the intersection point is 3, 2. That is the solution to the system of equations. All right, now let's do this again by graphing. Oh, actually, they've probably done this for us, so they graph this for us. We're not going to go through the graphing. It intersects at the point negative 1, 2. So that is our solution to the system. All right, let's try another one here. I'm going to rearrange the first one so it's in slope-intercept form. Okay, so I've got a slope now. Do you remember this is a slope of 1 over 1? Up 1 over 1, up 1 over 1. And that is not a very well-connected line, but... Okay, now we've got 10 here as my y-intercept. Now do you remember this is negative 2 over 1, so down 2 over 1, down 2 over 1. Okay, now this is the problem. It's hard to make those lines straight, but can you see this is where it was supposed to intersect right there? So our solution is the point 3, 4. So what's on this screen, I have never found this very important. What I want you to see is that if they intersect, it's got a solution. If they're parallel, there's no solution. And if they're on top of each other, there's infinitely many solutions. These terms here, I've never used them. I don't find them particularly important. I guess the only thing, inconsistent means no solution. But I don't use those, so it's not important to me. Okay, let's graph another one. This first one is already set up for us. I got it negative 6 is the y-intercept. Remember that. So that's negative 3 over 1 is the slope of this guy. So because I'm a little tight on space, remember you can give that to either one. You can give the minus to the top or the bottom. So I'm going to go up 3 and over 1. Up 3 over 1. Okay, now let's work the bottom one here. I've got 2y. Now I'm dividing that whole side by 2. Do you remember that that'll make this? So I divided everything by 2. So my intercept is negative 6. Well, you see actually this is the same slope and the same y-intercept. This is the same line. So we're going up through the same exact line. So this is all real numbers. Or infinite solutions, I guess I should say. They're both the same thing, but this is more appropriate here for this section. Okay, this one we start here at 2. Go down 1 over 4, down 1 over 4. All right, now let's solve this bottom one here. We've got 4y equals negative x minus 8. Now the 4 is going to go into both, so I'm going to get negative 1/4 x minus 2. Now my y-intercept is negative 2, but do you see I have the same slope in both of these? So I could build them, but you see we're going to have railroad tracks because it's going to be the exact same slope. Now my lines don't look like it, but the same slope, different intercepts, those are parallel lines. So they're never going to intersect at all. And this would be no solution. Okay, that's an introduction. The graphing, as you can see from my pictures, it's not very good because it's hard to make it look good and that you can precisely hit at the intersection of the graph. That's why we're going to learn a couple of other methods that are going to be much more preferred, but graphing does work, and it is one of the ways to find a solution to these systems where multiple lines are existing on the same graph.